Hello! So, Chapter 3, we're into two-dimensional kinematics. Chapter 1 is kinematics in one dimension. Chapter 1 is the physics fundamentals. Chapter 2 is kinematics in one dimension. Chapter 3 is two-dimensional kinematics. We're going to do everything we did in Chapter 2 twice, plus some of the stuff from Chapter 1 where we're doing some trigonometry. So remember, we decided we weren't going to be scared of trigonometry, so Pythagorean theorem, a squared plus b squared equals c squared, allows us to solve for the hypotenuse if we know the two sides of the triangle. Plus, we have all our trig functions, SOHCA, TOA, sine theta equals opposite over hypotenuse, cosine theta equals adjacent over hypotenuse, and tangent theta equals opposite over adjacent. So we have all those tools available to us. So remember that scalars are numbers with units. So speed is a good example of a scalar quantity. If you say that you're traveling at 25 miles per hour, that might not be terribly informative. Whereas if you say that you're traveling at 25 miles per hour straight toward me, that would then be a little more informative, and that would have magnitude and direction. That would tell me how fast you're moving and the direction that you're moving in. So if you ask someone where the library is and they tell you the library is a half-mile away, they're not necessarily being helpful because the library could be a half-mile in any direction. More helpful would be to say the library is located 1/2 mile away at an angle of 45 degrees north of west. Well, that might be kind of weird, but at least it would be helpful if you had compass points and you knew the directions that you were going in. It might also be awkward if you had to then cut through people's yards to get to the library. So we want to resolve that vector into its two components. That half mile at 45 degrees north of west has an x-axis component where you would walk down Birch Street for some distance, and then you would turn right and travel the y-axis component up 2nd Avenue to get to this fictitious library. So that's what we're going to be doing, resolving vectors. It's an important tool. So we have vector addition. So when you add vectors, you add them from the tail to head method. And we either do two vectors in a straight line, in which case they either just add them or subtract them like you would any numbers, or maybe they're not oriented in the same axis, in which case we have to do vector addition. Vector addition, we do the Pythagorean theorem, a squared plus b squared equals c squared, and we have to identify the direction that's involved, the angle theta, and then tell us where that angle is directed. So when you talk about the angle theta, here we have 4 vectors that are being described, but we're wondering if any of them are equal. Well, vector A, 100 meters, 30 degrees north of east, if you figure that you have the orientation, the coordinate system north, south, west, and east, then if you draw a vector that is 100 meters long, 30 degrees north of east, there it is. That's the vector. It has magnitude and direction. Vector B here, 30 degrees south of west. Well, I'm going to face south, and then I'm going to face west, and then angle south for 30 degrees, and then travel 100 meters. That's going to be pretty much the opposite of vector A. Vector C, 50 meters, 30 degrees south of west. Well, that's going to be the same as vector B, but only half as long. And then vector D, 100 meters, 60 degrees east of north. So I'll face north, the positive y-axis, and then I will angle 60 degrees down toward the x-axis, positive x-axis, 60 degrees toward the east. And it turns out that vectors A and D actually perfectly overlap each other. Now, typically, we will orient ourselves according to the x-axis. So we'll say north of east or south of west. We wouldn't normally say that something is east of north or west of south or something. That's just a little bit awkward. Alright, there's a triple jump on a checkerboard. I only show this example to make the point that you can do vector addition like this, but the point that we want to get is what the resultant vector is from square A all the way up to square B. So we'd say that's 2 squares over 2 times 4 centimeters, and then 1, 2, 3, 4, 5, 6 squares up, so 4 times 6, and so we'd have the x and y displacements, and then we would do vector addition in order to find out the resultant vector for this situation. Another example sometimes used is if you can measure the distance away you are from an object, a tree, a super tall building, I don't know, a model rocket that you launch up into the air. If you can do that, then you can figure out how high that thing is, because you know your adjacent value. You know the x-axis value. So if you can measure the angle for your line of sight, you're then able to figure out, by way of tangent, tangent theta equals opposite over adjacent. So opposite equals adjacent times tan theta. So if you have the angle and the distance, in this case we have the angle of 20 degrees, the distance 32 meters, we can figure out the opposite value, and then this question is just a little bit tricky because then we add in the 1.83 meters because the observer's point of view is already 1.83 meters higher than the ground level. Alright, so two-dimensional kinematics. This is where we really get into it. It turns out that if I had a rocket ship stored in my basement and I had 2 different thrusters on it, I would take it out and I would press the x-axis thruster button and I would travel in the x-axis. I might have an initial velocity, I might accelerate, I'd travel a certain distance at a certain final velocity, all that stuff. All of my motion in the x-axis if I press that x-axis thruster button. I could also press my y-axis button. If I did that, then my position would change according to the acceleration in the y-axis, and both of these are one-dimensional kinematics, just like we did in Chapter 2. It's just simple, straightforward, two-dimensional kinematics. But what happens if I press the button for both at the same time? Now my rocket ship is following this kind of curved trajectory, but it turns out, even though that's the motion that we would observe, if we looked really carefully, the x-axis motion occurs exactly as it would have if I had only pressed the x-axis thruster button, and the y-axis displacement, velocity, all of that happens exactly as it would have if I'd only pressed the y-axis thruster button. So that's the punchline with two-dimensional kinematics, that the motion in the x-axis is independent of the motion in the y-axis, and the y-axis independent of the x-axis. Those types of motion happen exactly as they would have if the other one wasn't going on. So if we press both buttons at the same time and we have a final velocity 98 meters per second in the y-axis, 190 meters per second in the x-axis, then we can find the velocity, the final velocity, this one, the final velocity, a squared plus b squared equals c squared. So this value equals the square root of 98 meters per second, so 98 squared plus 190 squared is some big number. Take the square root of that. I get 214 meters per second. That's the straight line final velocity. It's the vector sum. And then I can figure out the angle for that if I want to as well. Now, why we talk about this is to get into different applications in physics. One of them depicted here is relative motion. Relative motion is a vector sum. So we have the person on the train car who's walking forward on the car at 1.2 meters per second. They look down at the floor, their feet are moving forward on a floor that appears to be stationary, and they're traveling forward in the positive x-axis at 1.2 meters per second. In the meantime, the train itself is also traveling forward at 15 meters per second. So in that case, the person's relative velocity relative to a stationary observer on the ground is going to be the vector sum, and the vector sum is just the sum. We add the two numbers together. 1.2 plus 15, 16.2 meters per second in the positive x-axis. The opposite of that, if they happen to be walking backwards on the car, well, if they're walking backwards toward in the negative x-axis, then the vector sum is negative 1.2 plus 15 for positive 13.8 meters per second. Their net velocity is still in the positive x-axis, even though they're walking backwards. You can do fun experiments with this on the moving sidewalks at Logan Airport, where maybe the sidewalk's moving at a certain velocity and you really want to get to your plane as fast as possible, so you walk forwards, and then when you glance to the side you see, wow, I'm really moving fast here because the sidewalk's moving and you're moving on top of it. You can also do the thing where you turn around and walk the other way, and maybe if you walk fast enough you actually stand still. The sidewalk's moving at one velocity, but you're moving in the negative x-axis at that same velocity, and so your net velocity is 0. I guess that's the whole idea behind a treadmill, huh? Alright, well, that's not too difficult, so it's my job now to make it more difficult. The more difficult situation comes about when we do vector addition and the two vectors aren't oriented in the same axis. So here we have the person climbing up the car. So they're climbing up a ladder on the side of the boxcar. So they've got a positive velocity in the y-axis, while the train has a positive velocity in the x-axis. It's important that we specify what we're talking about. So those two little subscripts that you see, the velocity of the person relative to the train, and their velocity relative to the train is in the positive y-axis. They're climbing up that ladder. Also, we have the velocity of the train relative to the ground. That's in the positive x-axis. So the vector sum, we're going to make the inner and outer subscripts match. So the velocity of the person relative to the train plus the velocity of the train relative to the ground gives us the velocity of the person relative to the ground. So the stationary observer, if they're just focusing their eyes on that person climbing up the car, sees them moving not just in the x-axis and not just in the y, but the vector sum of the two, sees them kind of climbing up at a diagonal like that vector is depicted, the VPG. That vector is depicting pretty much the pathway that the ground-based observer would see the person traveling. That is vector addition. Now we're going to apply it to projectile motion. And before we get to projectile motion, let's take this relatively simple case. I have this airplane that's dropping a care package to the poor students trying to study physics at Salem State. It's dropping off snacks and coffee. And so it is flying in the air horizontally at 115 meters per second, and then it releases the package. It doesn't throw it down, it doesn't lift it up, it just lets it go so that it falls down according to acceleration due to gravity, what we talked about when we did one-dimensional kinematics with the y-axis, and then it falls down to the ground. Now we pretend, and this is a little bit of a lie, that there's no acceleration in the x-axis. We're going to ignore air resistance and just have this package fall down, accelerating at 9.8 meters per second squared as it goes down, and then not accelerate at all in the x-axis. It's going to keep traveling at 115 meters per second in the positive x-axis forever and ever, or at least until it hits the ground. So, we want to figure out what its final velocity is. So we list our knowns and our unknowns. We know that the initial velocity in the y-axis is 0 meters per second because it was dropped. It was released from rest in the y-axis. We also know that there's acceleration in the y-axis, the acceleration due to gravity, negative 9.8 meters per second squared. And we were given a value for the displacement. It's going to fall a distance of 1,050 meters, which means that its displacement, its final position, minus its initial position. Its final position is 0, ground level, and its initial position was positive 1,050 meters, so its displacement is negative 1,050 meters. There's our three knowns. Our two unknowns are the time that it takes to fall down and the final velocity. Let's make this really clear. When we talk about the final velocity of the package, we're talking about the final velocity the instant before it hits the ground. We're not saying, oh, its final velocity is 0 because it must have hit the ground and crashed and stopped moving. That's not what we're talking about. It wouldn't make sense. If that package hit you on the head, you would be injured. You wouldn't say, oh, the final velocity was 0. You'd say, man, that thing was moving at, I don't know, 50 meters per second when it hit me in the head. You probably wouldn't even say that. You'd just say, ouch, but pretend that you would say something. So in this case, we have our 5 kinematic variables represented. We don't know the time. We don't care about the time. So when we look at our equations of kinematics, we want to find the one that doesn't have time in it, because we're not looking for that. And so v squared equals v naught squared plus 2ax. This is pretty good because the initial velocity is 0, so v squared equals 2ax, so v equals the square root of 2ax. And so we get a velocity of 143 meters per second. Actually, that's not exactly true, right? If we do the square root of 2 times negative 9.8 times negative 1,050, take the square root of that number, the answer isn't really 143. That's what it shows me on my calculator. But the real answer is plus or minus 143. So it's up to me as the physics student to say, oh, you know what? That thing was moving down. That's negative 143 meters per second. That's the thing that makes sense physically, is that it was actually traveling down at 143 meters per second. So ultimately we're looking for the resultant vector, the vector sum. So we have 115 meters per second directed in the positive x-axis, 143 meters per second directed in the negative y-axis, and the vector sum a squared plus b squared equals c squared will give me the resultant vector to be 184 meters per second. Is that positive 184 or negative 184? Oh, x is positive, y is negative. Well, positive or negative doesn't make sense in this context because we're talking about a vector sum. It's not oriented purely in the x or purely in the y, so there's no way to say it's positive or negative. So the direction part, it's 184 meters per second, and then the direction part is an angle. The angle theta we would get by inverse tangent of opposite over adjacent. 143 divided by 115 gives me the angle 51 degrees south of east, or if I just wanted to say angled 51 degrees below the x-axis, or below the positive x-axis, I could say, so that I would face along the positive x-axis, then angle 51 degrees below it, and that is the direction for that vector. Okay, coming up next on the quiz on this material, On exam 1, and if we were to have a final in this course, on the final would be a question like this. This picture, different numbers, these words. You're at a football game, the ball's kicked with an initial velocity of 25 meters per second at an angle of 40 degrees above the ground. What is the maximum height the ball achieves? How much time does the ball spend in the air? And what is the x-axis range? This is the most important thing ever, to resolve our x and y velocity vectors and apply them to this kind of situation. I will ask you about it, and I will ask you about it again. The next video on here is a discussion. It's called The Most Important Thing Ever, and I walk you through the process. So, watch that one too. Time to shut this off. See you soon.